Right, in this example, we're told we have an airstream approaching a normal shock at a particular Mach number. Let's sketch this out. So we have a shock wave, airstreams coming in at a Mach number of 2.64. We also know the upstream stagnation pressure. That's 3 megapascals absolute. And we also know the density upstream, 1.65 kilograms per cubic meter. And we're asked to determine the downstream Mach number and the downstream temperature. Okay, so to determine the downstream Mach number, we can just simply go to the normal shock relations. So from the normal shock relations, and these are derived in the course notes. I'm not going to do that here. I'll just give you the final relations. But the downstream Mach number can be found from the upstream Mach number using this relation. And so we know the upstream Mach number. We know the K. K is the specific heat ratio for air. So the specific heat ratio for air is 1.4. It's a good number to remember. And we can solve this for the downstream Mach number. It should be subsonic, and indeed it is. So just remember that shock waves only form in supersonic flows. So we have an upstream supersonic Mach number, and then across the shock wave it becomes downstream subsonic Mach number. Okay, now the next step is to determine the downstream temperature. And so there are different ways to do that. The way that I'll use here is we're going to start from the density. We're going to use that density information, the rho 1, to find the stagnation density. And from the stagnation density and the stagnation pressure, we can find the stagnation temperature. And we know that stagnation temperature remains constant across a shock wave. So that'll give me the stagnation temperature downstream. And once we have that stagnation temperature and the Mach number downstream, we can find the static temperature. Okay, so I'm going to use the isentropic relations to find the stagnation density upstream. That comes from this expression. Remember, you can use the isentropic relations upstream of the shock wave as well as downstream. You just can't use them across the shock wave. So here we know rho 1, we know the Mach number 1, so we can solve for the density, the stagnation density at 1. So the upstream stagnation density, and that comes out to be 14.6 kilograms per cubic meter. From that, we can find the upstream stagnation temperature. This comes from the ideal gas law, so ideal gas law. So this will be P naught over rho naught 1 times R. Okay, so again, this is from the upstream. We know the upstream stagnation pressure, that's given right here. We know the stagnation density upstream, that's we just calculated. And the gas constant for air, we know as well, that's 287 joules per kilogram Kelvin. That's another good number to remember since we use it so frequently. So the upstream stagnation temperature comes out to be 714 Kelvin. Then across the shock, the one thing that remains constant across the shock is the stagnation temperature. That's the one property that remains constant. So the stagnation temperature on the downstream side of the shock is also 714 Kelvin. And from that, we can then determine the static temperature across the shock using this adiabatic relation. So this is on the downstream side of the shock. We know the stagnation temperature now. We know the Mach number downstream. We calculated that earlier, so we can find the static temperature downstream. And that static temperature should be larger than the static temperature upstream. I guess we don't have it, what the static temperature is upstream, but we know that across the shock, the temperature will increase. The stagnation temperature remains constant, but the temperature will increase. The last thing we'll do, we weren't asked to do this, but let's just go ahead and sketch this on a TS diagram. So let's say this is the stagnation temperature. That's the T naught 1, which is also equal to T naught 2. And here's our stagnation pressure upstream. So we're starting, well, we're not starting there, but that's our stagnation conditions. And we're starting somewhere here. Here's our T1 and our pressure P1. Let me put the pressure on the other side. So there's P1. So here's where we're starting at, just upstream of the shock. And then across the shock, we know that the pressure will increase, the temperature will increase, so that'll put us on a line, and also the entropy will increase. So we'll be somewhere along this line here. So this is the specific entropy upstream, specific entropy downstream. Like I said, the temperature will increase. So here's our T2, and then the pressure will increase. So this is our P2 here. So you can see that we go like that across the shock wave. So here's our state 1, here's our state 2. So the pressure has gone up. You can see the isobar here for P1, and then the isobar for P2 is a little bit higher. And then the stagnation pressure downstream of the shock is right here, P02. It's the same stagnation temperature, but the stagnation pressure is less than the stagnation pressure upstream of the shock. But that's this line from 1 to 2 is our process, just crossing the shock wave. I drew it as a squiggly line because this happens in a discontinuous way, because we're treating the shock wave as being infinitesimally thin, so it just suddenly jumps from 1 to 2. All right, that covers everything for this example, so we'll end there.